Okay, so good afternoon. It's nice to be here today with Stefano Serra-Capizzano. That's an honor to have you here in the Institute. And he's a good expert of numerical linear algebra, numerical analysis, a lot of numerical methods. And he was director of departments in the President Facoltà. Dean of faculty in Insubria. And we met many years ago because we have a common interest in mathematics for cultural heritage. And our common experience is to follow the career of Dr. Semplice, who was a collaborator and now is collaborator of the Institute for the Supreme Project with availability. And so we have this passion for this kind of difficult problems where a lot of different techniques are involved. So it's a pleasure to have him here today. And so we share the presentation now. Okay. And the title is Updating the GLT Analysis, New Tools and Beyond. So, Stefano, this is your topic.
Thank you very much, Roberto, for the nice introduction. It is an honor for me to be here, not the opposite. And Roberto was telling me, pay attention because here the interests are heterogeneous, there are people from physics and blah, blah, blah. And he knows that I like a lot of theoretical things. And then I decided to present something very theoretical, just to disappoint him. It is this theory of generalized local Toeplitz, but I will try to be not technical, just to pass the ideas.
Look here, okay. From Naples, we have the Pasquadama is following.
So I will try to pass the idea, not technical things, but just the ideas. So, which is this theory? Essentially, it deals with the sequences of matrix sequences. So, when you have a partial differential equation, an integral equation, integral differential, or the new object fractional differential equations, which are very trendy now, you use your preferred discretization technique, and you end up with some large linear system. But if the finest parameter tends to 0, then you have not just a coefficient matrix, but a sequence of coefficient matrices. So this is, I think, common in numerical methods. So which is the message? The message of this GLT theory is the following. Since this matrix sequence is related to some discretization method and to a specific mathematical model, one should expect that the singular values of this sequence or the eigenvalues of this sequence are not just a random object, but they have some regular features. So this is somehow expected because there is a continuous operator behind. So if everything is random, probably the discretization is not good. So what is this GLT? Is a way of describing this regular behavior. And the message is the following. Whatever is the partial differential equation or fractional differential equation, what is the discretization method of local type. Could be finite elements, finite differences, finite volumes, isogeometric analysis, not important. Then there exists a function on a given domain, and this domain will depend on the partial differential equation and on the method that you are using, such that a uniform sampling of this function will give you asymptotically the behavior of the singular values. This is very, very, very general. There are, for finding exception, you really need to create something pathological. And if the matrix sequences are Hermitian, then this symbol, the GLT symbol, will describe asymptotically the eigenvalues. So this is the main message, and this is one of the first things that I want to pass. Then, second point that maybe is good to emphasize, these GLT sequences form a star algebra. Who cares about this? The nice feature of this mathematical property is the following. Okay, you have two matrix sequences in this class. You make a linear combination, then, miracle, the symbol of the linear combination is the linear combination of the symbols. So this is nice from one point, but if you think, it is counterintuitive, because one thing that we teach to the student is the following. If you have two arbitrary matrices and you make a linear combination, there is no way that the eigenvalue of the linear combination are the linear combination of the eigenvalues. And this is false, of course, also for singular values. But when there is a discretization of a differential operator, it falls in this class for which asymptotically this is true. Linear combination. But it is a star algebra. So it means that you take two sequences again. Instead of considering a linear combination of the two sequences, you take the pointwise product. Then the symbol will be the product of the symbol, which is again something very magical, because if you have something in the class, some order in the class, then the symbol of the product will be the product of the symbols. And it goes till the inversion. So you take a sequence. There should be an assumption, at least with the inversion. Otherwise, it is false. You are cheating us. What happens? If the symbol has a set of zeros, which have zero Lebesgue measure, so does not vanish too much, then the pseudo inverse, or the inverse if the matrices are invertible, form a sequence, and the symbol is the inverse. Now, this is very theoretical, maybe at least it is clear from the starting of the presentation. I like theory, but maybe you are not excited by this. But think to a numerical method, think to a linear system that you want to solve. Then, if the preconditioner is in the same class, then Pn minus 1 times An will have the symbol given by F divided G, where F is the symbol of An and G is the symbol of Pn. So if you have found a preconditioner, so should be easy to solve, cheap practical things here, but it belongs to the same class and it has the same symbol, then the ratio will be 1 and all the eigenvalues will cluster around 1. So the theory can be used in a practical way. So now, just for jumping on something which looks strange, clustering. So you take epsilon, you go around 1, it means that the eigenvalues outside this disk centered of 1 are small of the dimension. When you are lucky, it is a constant. When it is a constant, then the Krylov method, preconditioned, will have a constant number of iterations independent of the matrix size. So the optimality, the best you can obtain. But often the cluster is weak. So you do not have in practice what you want. Then you can use the GLT stuff for approximating zero order. Then, since having cluster at 1 means that the preconditioned matrix can be written like identity plus small norm plus small rank, you make some machinery, machine learning, for learning the rank correction which will improve. So you will use the GRT theory for having a zero-order approximation, then you can improve it. So it is theoretical. I like it for this. This is clear, but the practical application are also interesting. Then maybe I should spend later some word more on why it is called locally Toeplitz. Or maybe I do now. You are used with the approximation of the differential equation. So go in the very basic setting of equispacing grid, maybe finite differences, maybe constant coefficient. You end up with Toeplitz. Toeplitz means that the matrices are constant along the diagonal. But now, if you have a Laplacian.
So they have already a very strong algebraic structure.
Yes, yes. But so this work, in fact, was motivated by Brezzi. Because when I met him, I was very young, it was 30 years ago, he told me, Toeplitz are beautiful, but come on, if you have a domain which is not square, if you have non-constant coefficient, if you have not uniform, then the structure is destroyed. It is enough that one of these conditions is not met, then the structure. So you are playing with a beautiful toy, but it is very limited. So the idea was to have a general theory including all these variations. So diffusion, non-constant. Then you have not a constant on the diagonal, but you have a sampling of a function if you think to finite differences. And the matrix is n by n. Then you have to imagine a microscope. I will look a subpart of this matrix of the square root of n size. It means that the evaluation of the diffusion will be in points which are close, because there are at most of distances square root of n divided by n. So it means that if the function is continuous, then locally is Toeplitz. This small square root part will be almost Toeplitz plus a small norm correction. This is the idea of the locally Toeplitz. You have locally recognize the derivative, which is Toeplitz, but globally is not.
And like the difference between a Riemann manifold and a flat space,
Exactly.
Euclidean space.
Exactly. The idea at the end is exactly the same.
Okay.
So now I have to do like this. No. Yes. So books. So here criticism will arrive, because why more than one book on this thing? And here maybe I should answer with Shakespeare when he makes tell to a character, there are more things in heaven and land than in your philosophy. Which is the message? You are a mathematician. No, we go back to our world. We create a theory and we make it very general. Then you will discover an application which will give you a challenge, something which is outside. So somehow the various aspects of these books treat the case where the symbol is a scalar valued function in one variable. Treats the case of multivariate symbol. This happens when you have partial differential equation in a general domain. And then, if you use finite elements, degree 5 and regularity 0, and you are in one dimension, then you will end up with the symbols which are 5 by 5. So they are matrix valued. And if you use finite elements, degree 5, regularity 0, in a domain of dimension 3, then the symbol will be 5 to the power 3 sides. It means that the eigenvalues of this matrix will be described by a matrix valued symbol, which means that there will be 125 different functions, the eigenvalues of the symbol. Because if the symbol is a function, all the eigenvalues will be a function, and n divided by 125 will be described by the first function, n divided by 125 by the second function, and so on. So the generality was not a choice, was induced somehow by the applications. Even if I like the application because one can solve beautiful problems, like the nonlinear modeling, which was also degenerate for the monument degradation. But it is interesting that for me, the value as a mathematician of the application are the challenge to theories. You make a theory, and then there will be something which is not included. Okay, so in part I said already this, so we somehow read now. Continuous infinite dimensional problem, I made the list. Suitable numerical approximation. So this theory is general, not only finite elements, finite volumes. So the shape of the function will depend also on the use of the scheme, but there will be analytical properties which are in common and which are decided by the problem. For instance, if the dominating operator, differential operator, is a fourth derivative, you expect a minimal eigenvalue going to 0, like 1 to n to the power 4. If it is a alpha derivative fractional, it will be 1 over n to the power alpha. This is independent if you are using finite differences or finite elements, but the shape of the function will change. There will be things in common because they are talking of an operator. So structure inherited from the continuous part, large dimension, and spectral feature described via a proper symbol. The goal, because I have to set myself as for applied goals, solving the resulting linear system by optimal methods. Optimal in this context means that the operation count for obtaining the solution should be of the same order of the matrix vector product. So if you have banded, like in local methods, you want linear time. So multigrid are an example of this class. Understanding the spectral property of the resulting matrices is also a goal, and also this is obtained by this symbol. This, yes. So linear partial differential equation, numerical method. You end up with this. If it is nonlinear, like it was in our case, then you end up with a sequence of nonlinear problems. You make some kind of linearization at a certain point, you will discover that the sequence of the Jacobian belongs to this GRT class, which was the thing that we used in that context with Matteo. So the GRT sequences are a tool for computing this spectral symbol, and somehow I anticipated why. Since it is a star algebra, you have your difficult magic sequence because it is not written in this language. You make a discretization, you obtain something, but if you are able to write this something like a product of simple things plus linear combination of simple things of which you know the symbol, then you cook the symbol by assembling. This is the idea.
Maybe I should have already understood, but I miss what is C. What is this?
It is, I told you, a function describing asymptotically singular values in the general case, and eigenvalues, there should be some assumption.
I should think of the symbol as a function.
As a function. You make a discretization on the domain of the function, you take the values. These values, if it is scalar value, make the modulus, are up to a small error the singular values. You take the values are up to a small error the eigenvalues. So it is non-trivial because if the size is very big, the approximation is better, which is the opposite that you have in general. So you have a large matrices, the eigenvalues are random number. No, they form the image of the function. Okay? So this was the main message. Okay? And then if you take a
because in fact you are discretizing a limit operator.
Exactly.
So clearly you have a trace of this approximation
Exactly.
in your metrics.
Yes, but the nice thing that was not completely expected, maybe is expected a posteriori, is that you make a linear combination of two objects of this thing, the eigenvalues just make the linear combination, singular values the same. This is somehow not expected, because it is against what we teach to the students. The students would have understood this if we do not spoil them telling that
unless you are taking algebras that is powers of the same matrix.
Yes, exactly.
Yes.
So somehow this is telling you that hidden there is some algebra asymptotic which describes this object. There should be something like this. But it's funny because if you look from this perspective, you have more generality than if you start from the continuous. This is another message. The other message is the following. The analytical problem is easier. The discrete problem, asymptotical, has more degrees of freedom. So you would have more information doing like this. Okay. So large dimension implied that direct solvers have to be avoided. Optimal iterative solvers. So the optimality notion was number of operations for solving the linear system of the same order of the matrix vector product. Then operation count per iteration, of the same order of the matrix vector product, and number of iterations bounded by a constant independent of the matrix size. This is often obtained if you have information on the spectrum. So this gives you the motivation. Because I started, as Roberto was saying, as a numerical linear algebra. So the goal was to find the fast method for the linear system. Then I thought the theory was interesting to study, and then I fell in love with the theory. We are what we are. I'm not guilty for that. Okay? And this symbol will give you information also on the unconditional subspace, which are, for instance, we will see that this function in the text setting will have a f which is defined between 0 and minus pi and pi. If the 0 of the symbol is obtained at pi, it means that the ill-conditioned subspace is made by high frequency. If it is attained at 0, then the ill-conditioned subspace is low frequency, and this happens for differential operator. For integral operator, it happens with I, and this explains why these are ill-posed problems, because a bit of noise will perturb where the matrix is very ill-conditioned. This is less severe for partial differential operator. So you have a lot of information. So main items, of course, I will not describe everything because Roberto, I'm interested in making you understand.
That's my fault.
Eh?
That's my fault. You have no time to describe all
No,
the items. No.
It's your fault because you told me that there should be something more practical, and then I decided to make the opposite of what you recommend. Just for stressing you.
Okay.
And so I will describe only how this GLT class is done. Because at the end of the seminar, if one has understood something, it is a goal. If I present many things, then nothing will remain. So I will try to focus on how this algebra is made. Because until now, it's like selling carpets. I've given you a lot of information, but just talking. Mathematics is mathematics. So we have to do something. Okay? So applications, there are many applications. As I told you, also machine learning when you use for improving the approximation. We tried this thing in many situations, for which, for this reason, I'm telling you that I believe that it is kind of general. So we solved many kinds of problems using this theory, and we arrived to a description of the spectrum asymptotically and to reasonable numerical methods which were optimal using this spectral information. Okay. Now, a little bit of mathematics. So we jump from the carpet to something concrete. So, matrices of size m, this is the space where the symbol will be. Because as I told you, depending on the kind of discretization, the symbol could be scalar valued or also matrix valued. So it's the application that tells you that this generality is needed. Sequence of matrices, this you should think like the sequence arising from your discretization method, from the ALLA discretization method that it is made. Size, increasing sequence of integers. Of course, they are not in sequence because if you have a strange domain, they jump. This is evident, we know that. Then psi is the candidate symbol, measurable on some domain in Rg with G larger than 1, and psi is ms valued with S larger than 1. The only constraint is the domain should have a measure not collapsing to 0, is measured not to infinity. And when we write this, I will give the definition, but the informal meaning, when we write this, if S is equal to 1, so the symbol is scalar valued, so there will be only one function, then if C is continuous, then a suitable ordering of the eigenvalues in correspondence with the replacement grid of this D reconstruct approximately this surface. If S is larger than 1, then C is ms valued, so it will have S eigenvalues because it is a matrix. Then the eigenvalues, when I write this, it means that dn divided by S behave like the first eigenvalue, dn divided S behave like the second eigenvalue, and so on. This is the okay. Okay, so this was informal, still is carpet-like. The formal definition is this Weyl distribution. So you take your matrix AN, you take any continuous function with bounded support, and you make this average, 1 over Dn, sum of capital F on the eigenvalues. Then we say that this is distributed like this if this discrete average converges to an integral. This is the formal things that in the case that psi is continuous is the informal meaning was described before. Okay? And if we write this sigma, so singular values, then you do not consider eigenvalues but singular values, and you will not consider the psi here, but the modulus of psi. So if it is scalar valued, we know what is modulus. If it is not scalar valued, psi star, psi, so transpose conjugate times to the power of 1/2. This is the definition.
Sorry, just a question. Maybe I don't understand, but if you have, for instance, a symmetric matrix.
Yes.
So in this case, we have a spectral calculus. So you can compute the function on the spectrum of the matrix. Coincide with this one or not? I mean, this value is a sort of
so if you have
spectral evaluation.
Yes, yes. But we say this is a definition. We write this if this limit holds for any f continuous with bounds.
Okay, this is the case when you have no spectral theory because AN is not symmetric.
Yes, in general.
But in the special case, it coincides.
Yes. Okay. So this is what I anticipated. So you take just a Laplacian. Laplacian in the dimension. Then, if you consider finite elements of degree p and irregularity 0, then the S was the this S here, the size of the symbol. Clear enough? No. The S is P to the power 10. So this explains why, from a numerical linear algebra point of view, I order in P finite elements give trouble to numerical solver for linear system, because the spectrum is made by an exponential number of different branches. And according to the terminology of the engineer, only one is an acoustical branch, so describing the eigenvalues of the operator. The other branches are all optical, like mirages, so they are rubbish introduced by the method. So imagine P equal 5 and D equal 3. 124 eigenvalues over 125 are not approximating the operator, only a small part. Then, if you add C0, regularity K, then it is still exponential, but instead of P, you have P minus K. So the isogeometric analysis of commutes, which have P minus 1, you have S equal to 1. So there is only one branch, and it is acoustical. So Commux invented the isogeometric analysis for making communicate the computer-aided geometrical design for describing the objects with the space of the finite elements. This was but there is a kind of revenge of the regularity. This regularity makes the structure of the spectrum of the matrix unbelievably simpler. Instead of having e to the power d function describing the spectrum, you have just one. So there is an advantage, which was not the thing for which Tom Hughes did that, but you understand by this theory. Okay? So this was an example with d equal 1. So I'm terrible. I claimed the larger thing, and the example are with d equal 1 because it makes no sense. They plot 125 functions with not single elements. Okay? Blocking systems, this is the beyond of the theory. So if you have a system of partial differential equation, not one PDE, a system of partial differential equation, or you have domain decomposition techniques, then each of these blocks will be in this GLT algebra. The question is, the global object will have still a function describing the spectrum. Again, the answer is yes, but I will not give details, so I will jump. Okay? So this was something, and we applied this to the organoid problem. So we made experiment with 1,000 of cells, which means 1,001 PDEs discretized, so you have very huge linear system, and still we were able to recover the spectrum and to obtain fast methods. Here it is really a HPC computing, even if I'm not expert. It was Beneduzzi and Ferrari doing most of the work. Okay, definition. So I promised you something less carpet. So definition. Definition. Weierstrass theory. You have a function and you want to approximate it with polynomials. No. Then the function is of some x, and the polynomial is also of some x, but there will be a small m. So like m tends to infinity, the Pm, if you are in a compact, is approximating the function uniformly. Okay? Here the idea is the same. If you want an approximation theory for sequences of meshes, you have to add a new parameter. So there will be a class of sequence. So every BNM is a simpler object with respect to AN. Okay? So maybe BNM is block diagram, let's say. And for some reason, I'm claiming that AN is approximated by BNM. And here there is a question. When you use the Weierstrass theorem, the F minus the polynomial Pm is small in norm. But if you have a large matrix, 1000 for 1000, and you make a rank 1 update, then you can solve very fast using an algorithm for the original matrix. So in asymptotic linear algebra, when the matrix size tends to infinity, the object which should be small in two different directions, rank and norm. So the right definition is this. B and M is an approximating class of sequence for the difficult matrix sequence if there exist two error terms, not one. One which is of rank which is relatively small with respect to the matrix size, and the other which is of small norm. By the way, this has a counterpart for functions? Maybe yes. Think to a function which is L infinity on 0, 1. And think, if you know, to the Lucene theorem. The Lucene theorem is telling you, for any epsilon larger than 0, there exists a domain of measure larger than 1 minus epsilon, such that f is equal to a continuous function depending on epsilon on that subset, and in the complement, it can be completely different. So this complement is the rank correction. In a small subspace, the two matrices are very different, and in a large and in a large linear space, the norm is small. It is the counterpart of the Lucene theorem. So if there is a good definition, there should be a good theorem. So this is a kind of commutative diagram. So you have an approximating class of sequences for AN. So it means that the AN can be written as the simple things plus small norm plus a small rank. Then the simple things, you know the singular value distribution like Cn. If you can check that Cn converges to Psi, then you can close the graph. So the idea is find something simpler on which you can compute the symbol. You make the limit of the symbol. This limit is necessarily the symbol of the difficult object. This is the foundation of this theory. So the basic is a kind of approximation theory for magic sequences. So it looks very abstract, but the idea of small rank, small norm is exactly what people are doing with preconditioning since a lot of time. Because when you say that the preconditioned matrix are all the singular values close to 1 except a small number, you are telling that in a large subspace they are almost identical, and in a small subspace they can differ. And the number of iterations is small. So this approximation theory result was induced by Krylov practical methods with preconditioning. Okay. And now we go to the components. And I will not explain how the star algebra is built, but I will explain how to construct this approximate, because it looks very accurate. So if I have a difficult magic sequence, how I can compute the simpler object. So start with Toeplitz. On Toeplitz we know everything, because as Brezzi was saying, there were a lot of people interested in this very specific object. Okay? So you take a function f, which is L1, so here in I to the power d, matrix value. Oops. Who cares? Imagine S equal 1 and D equal 1. You take the Fourier coefficient of this function and you put in the diagonals. This is nice to meet you, the definition of Toeplitz matrix generated by F. The nice part is that these Toeplitz matrices have a lot of properties, including the fact that PNF is distributed as a symbol the function f itself. Okay? This is something that is known in the literature. There is 100 years of research on this, starting from Toeplitz, Zego, then Widom, Parter, Vertishnikov, Avram, a lot of people worked on this very specific. So this is the case. So here, if you consider this and you want to reconstruct the function, is 2 minus e to the I theta minus e to the minus I theta. So the symbol is this. U, the eigenvalues in this case are magically equal.
Just by the way, this is the combinatorial Laplacian of a lattice.
Of a linear graph. Of a linear graph. If you have a lattice in many dimensions, it will be the sum of this with theta j. So these are the Toeplitz graphs, which are included in this.
We call it just path graph.
Yes, exactly. Then the distribution is known because someone worked on this. Now we take a class which is even simpler. So this looks very stupid. You take a function a from 0, 1 to c, and you consider the diagonal sampling matrix. So of course the eigenvalues are this and the singular values are the models of this. So for sure there is this distribution. You don't need to check anything. It's really stupid. Let's say, is a way of making complicated something simple. Okay? The nice thing is that these are the ingredients. So what is the GLT algebra? Now, I do not present how it was constructed. It was constructed using the theorem that I've shown before, via approximating class of sequence.
But have these algebra generators?
Yes, it's written here. So we could have a reading which is the mathematical one. Let's start with the reading I want to understand. The reading I want to understand is the same, is the following. The Toeplitz generated by F are in this GLT algebra, and there's F symbol, something which does not depend on space. It's just depending on F of theta. Okay? The diagonal are just only depending on space. So the symbol is A of x. And these are in the GLT class. Then there are the zero distributed, those which are clustered in the singular value sense at 0. You want an example? Discretization of compact operators. This gives you. These are the 3 building blocks. Then, since this is an algebra, then if n is GLT of k, automatically the star is GLT of k star. And maybe I should jump here. Linear combination, product, inversion when the symbol is not a different 0 almost everywhere. Then the pseudo inverse behave like this. By combining.
This is the Hadamard product, or just the classical product of matrices.
This is the classical product, component by component. So since it,
not the matrix.
no, it's not Hadamard. Since these are matrix sequence, you have to multiply at the.
Oh, I see. It's the big matrix.
Yes, it's the matrix sequence multiplied by the other matrix sequence. It gives you a matrix. So it's Hadamard in that sense, but it's not Hadamard. It's the standard product. Then the symbol will be the product. Then let's come back. Oops. Where are you going? This was all the rest of the presentation, but I will give this.
Very good. You are advancing.
Okay. No. I don't know how to go back.
You can.
Maybe.
This, not this. Okay, so once you have the 3 classes, you have this algebraic product, any linear combination product is still in the class, and you have the symbol constructed in the same way. Notice that if you start by a Toeplitz and you make inversion and multiply by another Toeplitz, this has no algebraic structure, but the spectrum remains. So the representation is lost. Okay, so the Toeplitz have a strong algebraic structure and strong spectral properties. This class, the algebraic structure is not seen. At the end, it will be a total mess, but inside they remember the origin of the structure. I don't know if, and here it is what can be said for eigenvalues. So if you have a Hermitian and you add anything, still you have the same distribution, but there should be some condition on the norm of the non-Hermitian part. This is useful when you have, for instance, some Laplacian plus first order terms, which are of course not Hermitian. The condition is that the Schatten norm 1, so the sum of the singular values divided by the dimension, tends to 0. This is something expected. So for making clear what happens, let us consider this simple case, which I anticipated. You know the terms on the diagonal minus E3 alpha, so it means A evaluated in 3 alpha times H, and H is 1 over N. We know this matrix. And here you see the locally Toeplitz structure, because if you take the first log n rows and the first log n columns, there are evaluation A on 3 alpha H, A on 5 alpha H, A 7 alpha H, until log n H. Come on, it's still something very close to 0. So locally it's Toeplitz. Okay? But the nice thing is that this
if A of X is regular, is smooth.
Yes.
Okay, if you assume that A of X is
but the nice thing is that the theory goes stretches until Riemann integrable. Okay. So you can have an arbitrary number of jumps. The only thing is that they have accumulation point. Okay. So it stretches very, very far away. Then you can write this as a DNA, the sampling of the stupid matrices I presented before, times the linear, the path graph. Oh, this is a GRT. This is GRT, and this is zero distributed because it goes to 0. Then the symbol is this. A of X times 2 minus 2 cosine theta. So notice, in the constant coefficient case, the function is in one variable, theta. In the variable coefficient case, you have 2 variables. And now also this is an interesting interpretation. There will be one Fourier variable and one space variable, which is not seen when it is constant.
A sort of pseudo-differential operator.
Exactly. In fact, my dream is to link the two things, because this is really the counterpart of pseudo-differential operator.
But you see, it's not done.
No, it's not done.
Okay.
This is not done.
Yeah, but because it looks like the symbol calculus.
Yes. So if A of X, you are in 3 variables, there will be A, X1, X2, X3, and here the sum of 2 minus 2 cosine theta J, J1, 2, 3.
Yeah.
If X stays in a domain which is a potato, the limitation is that the domain should be Riemann, Peano-Jordan measurable. So the characteristic function of Riemann integrable, which is extremely weak. Usually the applications are better. There is a piecewise Lipschitz boundary. So the theory really stretches. Then if this is the symbol. And now you make some stupid math, you compute Ln, you make a uniform sampling in 2 variables, you order, and they are almost coinciding. So here I have to remember Jean-Golub. Jean-Golub has been the greatest numerical linear algebraist in the world. He was very rough, very kind with young people, but sometimes very rough in the conferences. So there was a person presenting something, and he was talking about asymptotic convergence. And he said, who cares about asymptotic? In the long run, we will be all dead. So all this theory is asymptotic. So Jean-Golub, but at the end I collaborated with Jean-Golub. The point is that you see here the dimension 400. So the matrix is really a toy matrix, and you have an error of the order of 1 over n, which is not wonderful if you are a person from approximation theory that wants to approximate a function. But in numerical linear algebra, if your preconditioner makes a cluster of radius 1 over 10, is already ultra fast. So the nice thing of this theory is that it's ultra general and asymptotical. But for the context we are using, we don't need high precision. So this is the key for which it works at the end, also in practice. There are many things to say, but I think that I stop here, otherwise.
Okay. So.
I like to stay in the time.
No,
you are kind.
Okay, thank you very much. Have you a question? And even for the people connecting, we have a 8-person, 8-person now on YouTube. And if you have any question, you can write down in the comments. But anyway,
some estimates of the error rate. It is asymptotically, but you may.
Yeah, depends on the regularity of this A of x. If it is very smooth, it is 1 over n, which is not unbelievably good, even when this is like this C infinity. If it is less regular, it can become even worse. But there is an unbelievable thing. If I take, for instance, the Toeplitz generated by 4 minus 3 cosine theta minus cosine of 2 theta, then the eigenvalues of this can be written like this symbol on J pi divided by n with an error of 1 over n. And this is okay. But the unbelievable thing is that you can add 1 over n, and there exists a function which I don't know, but there exists. C1 J pi over n. Then there is 1 over n squared, then there is C2 J pi over n. I don't know this. I don't know that, but it exists and I can continue. So, extrapolation, like for Romberg. It means that we invented matrix-less eigensolver. You don't need even the matrix. You compute the eigenvalues on small matrices, and by making extrapolation, you compute the eigenvalues of very large matrices. So the analysis of the error is very interesting. So here it is another word. So there is not one symbol, but there is a hierarchy of symbols. One gives the first order, then the second order, the third order.
But you have still to compute the symbols anyway.
Not necessary, because when you make extrapolation with the integral, you don't know the constant. The extrapolation will compute.
Okay.
Okay, so you don't need to know C1 or C2. You make extrapolation, it is automatic. Then it is interesting in itself to understand what they are. This I agree. But in practice, now I'm playing the practical guy. In practice, you don't need to know the function.
This is a series, or
it stops to the regularity of the object. So there are cases of structured matrices in which apparently the eigenvalues are not known, but in practice they are so beautifully behaved that you can consider. In fact, the first paper on this with title, "Are the eigenvalues of Toeplitz matrices known in closed form?" The answer is no, but almost. So it is a funny thing. So, but this is not general when you have the A of X. So this is something which you should investigate case by case.
So the right answer is they are not known, but eventually they are.
Eventually they are.
Okay. Do you have any questions and comments? Curiosity? Anyway, thank you very much.
Thank you to you.
It was very interesting. I didn't know anything about that. Yeah. But I know pseudo-differential equation, para-differential equation. Exactly. So I found some similarities.
But this is my dream since 15 years to make a bridge between the two theories, because the format is identical.
Yeah.
So there should be a connection. But I'm not strong enough in hard analysis for me. So now I'm writing a paper of conjecture, full of conjecture, and this is one.
Okay.
Pseudo differential operator and GFT, how to combine the things.
Okay, so thank you very much. We can stop here.
Thank you.
Thanks again.
Grazie a voi che siete usciti.